All right, guys, let's begin week 4. Hopefully you've already printed your copy of the fill-in notes and are ready to fill in the blanks. So here we see our goals for this week. We want to be able to describe the location of electrons using electron configuration and orbital notation. And the second thing we want to do is be able to describe these patterns that we see, including atomic size and ionization energy. So these are two very big topics in chemistry. So we're going to do a brief overview and then you'll have time to practice those. So a little bit about the arrangement of the periodic table. Let me back up just a second. You want to make sure that you have your copy of the periodic table in front of you. If you haven't printed that out, now would be a good time to stop the video and do that. We're going to be labeling some things on the periodic table. All right, so let's go back to the arrangement of the periodic table. The periodic table is arranged in rows, horizontal rows, and these rows are called periods. And there's also up and down vertical columns, and these are called groups. So we can talk about the periodic table in terms of the periods, the horizontal rows, or the groups, the vertical rows. The periodic table can be divided into different groups. So the first group we'll talk about are called the main group elements. And as your notes say here, they're also known as the representative elements. They consist of the tall columns on the right and the left of the periodic table. And they are numbered 1A to 8A, or most modern periodic tables just number the groups 1 through 18. So with that kind of numbering, it would be 1, 2, and then 13 through 18. So those would be your representative elements. Next we have what are called the transition metals. These are the 10 short columns in the middle of the table, and they are numbered 1B to 8B, or on a modern table, they're numbered groups 3 through 17. Oh, sorry, no. 3 through 12. And then last of all, we have what are called the inner transition metals. Inner transition elements, and these are at the very bottom of the periodic table, kind of set alone by themselves. They consist of both the lanthanide and actinide series, and there's no group numbers assigned to them. So let's take a look at our table. Here in the previous notes we have talked about the periods and the rows, so you may choose to make some notes on your periodic table. Remember that the periods, that's not a good color, the periods on the periodic table go across this way. Periods are horizontal rows, and then the groups, they go up and down. Periods go across, groups go up and down. Let's take a moment to number our periodic table. The periods are not numbered. And so on the periodic table, there are 7 periods, and I would like for you to number them as such. N equals 1, N equals 2, N equals 3, all the way down to N equals 7. N 6, N equals 7. So the periods, again, the periods go across, the horizontal rows across. And so just to be clear, and you don't have to do this on your periodic table, but the first period includes hydrogen and helium. The second period, these two elements, and all the way across here. The third period, same kind of pattern. The fourth period, however, goes all the way across, and so on with period. And so that's how the periodic table is organized by periods. Now the groups, as we said, go up and down. And these numbers are kind of hard to see, but this is group 1, this is group 2, this is group 13, 14, 15, 16, 17, and 18. The groups in the middle, well, let's back up. Groups 1, 2, 13 through 18, the ones that I've numbered, those are your main group elements. The second part that we talked about were the transition metals. Transition metals are these short columns in the middle, all of these. There's 10 of those, and that's numbers 3 through 12. Those are transition metals. And then at the very bottom of the table, these two right here are the inner transition metals. And so this is your lanthanide series and your actinide series, and they're simply named after the very first element in that period. And these actually fit right here where these blank places are. These two rows fit in that part of the periodic table, and if those rows were in place, then the entire table would be shifted over. And so you would have an unusually long periodic table. And so the main reason they put these inner transition metals at the bottom is just so that the table fits nicely on the page. So this is the table, that modern table that we use today, developed by Mendeleev. We're going to talk about just a few of the names given to some of these groups. Group 1A, that's the one on the far left side of the table. These are called the alkali metals. And then group 2A, right next to them, are the alkaline earth metals. Alkaline earth metals. Just a few properties for each of these groups. Both groups have similar properties. They are metals, so they're shiny. They tend to be soft, which means that they're easily scratched. They have low melting points. They're good conductors of heat and electricity. We talked about the fact that conductors just means that it allows heat and electricity to flow through the material. And then when these metals react with water, they tend to form a basic solution, meaning a very high pH. A couple of the other groups that we will talk about is on the far right-hand side of the table. So we have group 7A, or that would be group 17. These are called halogens. And then we have group 8A or group 18. These are one and the same. These are called noble gases. Noble gases. So both of these groups consist of nonmetals. Some properties of halogens, they tend to exist as two atoms joined together. We call these diatomic molecules, which we'll learn more about those at a later time. Diatomic molecules. They are very reactive, and that has to do with the fact that they only need one more electron to fill their outer shell. Whereas noble gases are very stable, so these are like complete opposites, very stable versus very reactive. The reason that they're very stable is because they have a full, what's called an octet, a full outer shell. They have 8 valence electrons in their outer shell. And for that reason, they rarely combine with any other elements. All right, so that's the general layout of the table. The next thing we want to talk about are the electrons. We know that in the atom, in the center of the atom is the nucleus, and that contains the protons and the neutrons. But around the nucleus are the electrons. And so an electron is confined to a specific region around the nucleus, and that gives it a particular energy. And so the regions occupied by electrons are called principal energy levels. Another word for that is an energy shell. You may hear it referred to as a shell. an energy level, or a shell. The letter that is associated with a principal energy level is the letter N. N, just like we wrote on our periodic table above, when we were labeling the periods, we said N equals 1 all the way to N equals 7. So these energy levels correspond to the period numbers on the periodic table. So let's write that out to the side. This is the period number, N equals. So we've seen that these shells are numbered N equals 1 all the way to N equals 7. And again, they correspond to the period numbers. Electrons in lowered number shells are closer to the nucleus, and they have a lower energy. They are lower in energy. So lower number has lower energy. Higher number are farther from the nucleus, and they have a higher energy. So higher number, higher energy. Lower number, lower energy. All right, so we know what the energy levels are. Within the energy levels, let me back up, I'm getting ahead of myself. So shells with larger numbers are farther from the nucleus, as we said before, and they can hold more electrons. So the maximum number of electrons in each shell is given by this simple formula of 2n squared. 2n squared, where n is simply the shell number that you're referring to. So here's a chart with all of this worked out for you, but let's just say that you wanted to know about an element that was in period 2. So an element in period 2 has n equals 2 as its shell number. We want to know how many electrons could fit in that shell. And so we would take 2 times 2, 2 times 2 squared. 2 squared is 4 times 2, that would be 8. So in the second energy level, it can hold up to 8 electrons. Let's try another one. What if we wanted to know about shell number 4? So we have 2 times 4 squared, 4 times 4, 16 times 2 is 32. 32. So this is an easy way to be able to determine how many electrons a particular energy level can hold. All right, now moving on. We know about energy levels. Well, these energy levels, or shells, they can be further divided into something called subshells. Or I refer to them actually as sublevels. So you may hear me say the word sublevel. So these sublevels are identified by the letters S, P, D, and F. S, P, D, and F. Okay? And then these subshells actually consist of something called orbitals. Orbitals. An orbital is a region of space where the probability of finding an electron is very high, and each orbital can hold a maximum of 2 electrons. So we've introduced a lot of terminology here. Let's just break that down a moment. We're talking about where are the electrons, and so we can pinpoint the location of an electron, and we can get more and more specific as we look at these different levels. And so we start with the energy level. The energy level, and within energy level there are sublevels. Remember, the energy levels can be n equals 1 all the way to n equals 7. The sublevels can be S, P, D, and F. And then within each of these sublevels, we have something called orbitals. And within the orbital, you'll find the electron. And so we're just getting more and more specific as we move to a more precise location. So the chart is showing you how many orbitals each sublevel has. And so this would be an important chart to remember. The S sublevel only has one orbital. P has 3, D has 5, and F has 7. So this would be one to commit to memory. The next slide is just showing you the different shells or energy levels, as well as the corresponding sublevels and orbitals, along with the maximum number of electrons. So it's basically just putting everything we just talked about in one place. I have a slide here that shows you a couple of the different sublevels and the shapes of their orbitals. So the S sublevel only has one orbital, and it's a spherical shape, so just a round spherical shape. The P or sublevel has 3 different shapes, and they're given to you here. There's this PX, this one's PY, and this one's PZ. And this is what it looks like when all 3 of them are put together. And remember, each one of these orbitals can hold 2 electrons. So think of maybe an electron here, and there'd be an electron here, and maybe one here and here. And so that's a total of 6 electrons in those 3 p orbitals. The D and F sublevels also have some different shapes, but they're kind of complicated looking shapes and certainly hard to draw, so we'll just leave it at that for now. All right, so how can we use all this information to give an address for every electron in the atom? That's basically what electron configuration is. So the electron configuration shows how the electrons are arranged in an atom's orbital. So it is an address that tells where every electron is within the atom. We have something called a ground state configuration, and that's what we will draw mostly. This is the lowest energy arrangement. This is like the normal arrangement. And there are some rules that go along with writing configuration, electron configuration. And so let's go over these rules. Rule number 1, it says that electrons are placed in the lowest energy orbital first, and that always begins with the 1s orbital. The 1s orbital. And so after 1s is filled, then the orbitals are filled in order of increasing energy. And so this next slide kind of points out, think of this as a graph, and this would be the y-axis. And so you see the y-axis here is in terms of energy. So as we go up this graph from 1s all the way to 7s, the energy is increasing. And so if you follow these little small blue arrows, it's showing you the order in which the electrons will fill the different orbitals. So just like Rule 1 said, we'll always start with 1s first. And remember, each orbital can hold a maximum of 2 electrons. And so once 1s has its 2 electrons, then the next orbital that will be filled up would be 2s. And then we follow this arrow over. The next one would be the 2p orbitals, and then 3s, and so on. So you can kind of see how that's going to go. All right, let's look at rule number 2. So rule number 2 says that each orbital holds a maximum of 2 electrons. When orbitals are equal in energy, then 1 electron is added to each orbital, until all the orbitals are half filled. Then, and only then, the orbitals can be completely filled. So let's look and see what that looks like. Let me zoom in. Let's say that we have filled up electrons in 1s and 2s, these arrows. I'm drawing an arrow that looks like that and an arrow that looks like that. The arrows represent the electrons. And so once we reach the P sublevel, we know that P sublevel has 3 different orbitals. So this rule that we just read says that when the orbitals are of equal energy, so that's what we see here, the P orbitals, they all are equal energy, same amount of energy. So let's say we have 4 more electrons to fill in. And so the electrons are going to fill one orbital with 1 electron, and then it's going to go to the next orbital and put 1 electron, and then the third orbital and put 1 electron, and then it will pair up because I have 1 more electron to place, so it's going to go back and pair up with that electron. Remember, electrons have negative charges, so when 2 electrons are in the same, let me just back up. When the electrons are filling the orbitals, they prefer to be in an orbital by themselves because their charges repel each other. So we'll see in a moment that the reason that I'm drawing an up arrow and a down arrow is because when the electrons are in the same orbital, they're trying to stay as far away from each other as possible. So they tend to travel in opposite directions. And this is called the spin. And it just indicates the direction in which the electrons are traveling. All right, let's keep on going with our notes. There's something called an orbital diagram that I've been showing you. This is the name of it, where you see this little box and you see these arrows. So an orbital diagram uses the boxes, and once we start writing it, quite a few of these instead of the box, we'll just simply do a line, and we'll put our electrons on the line instead of in the box. So the box represents the orbital, and the arrows represent electrons. So when you have a single electron, it's 1 arrow. When you have 2 electrons in the same orbital, you do 1 arrow up and the other arrow down. And so 2 electrons must have opposite spin to fit in the same orbital, and that's indicated with the arrows, 1 arrow going up and the other arrow going down. All right, the next couple of slides just gives you some examples of the elements and their orbital notation and electron configuration. Notice the orbital notation shows the different orbitals, and the electron configuration, it simply just shows the principal energy number and the sublevel along with the number of electrons. So the first one is hydrogen. We know hydrogen only has 1 electron, 1 proton, 1 electron. And so the electron is going to fill the first energy level first, 1s. And since there's only 1, we just simply draw a single arrow. The next is helium. Helium has 2 electrons, and so both of those electrons are going to go into the first orbital. So we have an arrow going up and an arrow going down. If we take a look at electron configuration, this is just another way to write this, another format. In electron configuration, you have the principal energy level, you have the sublevel, which in this case is S, and then this exponent tells you how many electrons are in that sublevel. So this is pronounced 1s1. For helium, you have 1s2. Let's go on and look at some other examples on the second row. Lithium has 3 electrons. So in the orbital notation, we're going to fill 1s first. This is a typo. This should go here, so it'll correct that in your notes. Lithium's first 2 electrons are going to be in the 1s orbital, and then its third electron would go in the 2s orbital. So its configuration would be 1s2, 2s1 electron configuration. All right, here's another little typo. If you'll move that S up here. And let's go ahead and correct this. Sorry about that, I didn't catch it. All right, now it's written correctly. So let's skip down to carbon. Carbon has 6 electrons. And remember the order that we fill our boxes. We always start with 1s, and we put a maximum of 2 electrons. So 6 minus 2, we've got 4 more to go. So then we put 2 more in the 2s. So we have 2 more to place. They're going to have to go into the p sublevel. So remember, the electrons will fill one box with 1 electron before they start pairing up. So you have 1 electron in this orbital and 1 electron in this orbital. Here's our electron configuration. We have 1s2, 2s2, and 2p2. So hopefully you can see a connection between the electron configuration and orbital notation. It's the same, pretty much the same information, just written in a different way. All right, let me teach you about a shortcut. It's nice to find a shortcut every now and then. So the shortcut for electron configuration is called the noble gas configuration. Noble gas configuration. So if you remember our discussion of the periodic table, group 18, the very last group on the right, were called noble gases. And so in this noble gas configuration, we're going to write the symbol of the previous noble gas. Previous meaning the one that comes before. And then we're just simply going to add the electron configuration of the additional electrons. So here's what that would look like. If we take the element carbon, this is the electron configuration for carbon. And we want to write the noble gas configuration. So we're going to find the noble gas that comes before carbon, and so that would be helium. And go ahead and write its noble gas configuration. So it's just 1s2. And if you notice, these 2 atoms, these 2 elements, have this part of their configuration that's exactly the same. Both have 1s2. So this shortcut is simply taking helium and putting it in a bracket. And then when you do that, you're saying carbon's configuration looks exactly like helium's configuration, with the exception of this part. So you simply have to write what's different. 2s2, 2p2. So when we put the noble gas in the bracket, we're leaving out the part of the configuration that they have in common, and we're simply writing what's different. And so hopefully you can see this is helpful once you get to some of our bigger atoms that have a lot of electrons. And so this is just a shortened way to take care of that. All right, let's look at one more thing. We have the element calcium. Calcium has 20 electrons. So when we start looking at where these electrons are going to go, you can start with either the orbital notation or the electron configuration. Either would be fine. Again, this S should go up here, not below. There we go. Now it's correct. And so as you're drawing your lines or your boxes, keep track of how many electrons you've placed. And so we always start with 1s, and we're going to have 2 electrons. So we have that. Then next is 2s, those 2 electrons. So we've used up 4 of the 20. Okay, so we keep going. We're going to fill all of 2p, so that's a total of 6. And we add that to the 4 we had before, so that's a total of 10. So we're halfway there. Next is 3s, and it will hold 2 electrons. And then 3p, it'll hold 6 more. So we have 16, 17, 18, and we have 2 more to place. So we're going to put those in 4s. The electron configuration is written here for you: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And then last of all, the noble gas configuration. So we find calcium. Calcium is on period 4. So we want to find the noble gas that comes at the end of period 3, and that is argon. So argon has a configuration that looks just like this. And so we're going to put argon in a bracket, and then all we have to write is how it's different for S2. So that would be the noble gas configuration for calcium. All right, I'm going to stop the video here, and we will have part 2 at a later time.